Greetings everybody, it's been a while, hasn't it, since my last upload here on this channel. No, it hasn't been, it's only been 3 weeks. I've gone several months without uploading on this channel before. But yeah, got too many uni assignments to do and whatnot, and not enough time to do YouTube stuff. But we're back here again today. I'm at my university because we have these nice blackboards that we're going to try and use today. But yeah, what are we doing, by the way? Well, this is why I clicked on the video. We are doing the Laplace transform of a matrix. What on earth is the Laplace transform of a matrix? Well, I have no clue. Well, I guess I do have a clue because that's why I'm presenting it today. But yeah, this is probably something that a lot of people might not have thought of before. I was just thinking of ways we could mess around with matrices because we've done videos on the logarithm of a matrix, sine of a matrix, e to a matrix, what else? Matrix to a matrix, and matrix factorial. So why not the Laplace transform of a matrix? So we want to try to make sense of this today. So at the moment, this probably makes no sense whatsoever. But we can first start by recalling the definition of the Laplace transform. So if we have curly L over here, what is the Laplace transform? Well, the Laplace transform takes in a function that goes from R to R. Now, technically, it's R plus, including 0 to R, but just to save some writing, we can just say it's R to R. There's some other things we need to consider as well. For example, f needs to be of exponential type, which means you can bound it above by some kind of exponential function and all of that stuff, so you can actually integrate it. But yeah, essentially it's just a function from one real number to another real number. And what is the Laplace transform? Well, it gives us another function. And now this function goes from C to C. So we can take in complex numbers now. Our S variable that you see can be complex numbers. I'm pretty sure the real part of S has to be greater than 0. But yeah, we can just think about it as a function from C to C. Okay, and we can also write up the definition of the Laplace transform if we have curly L of our particular function f over there. Well, this is a function. It needs one complex variable, which we'll call s over here. And, well, this is just defined to be the integral from 0 to infinity. Well, we take our function, we evaluate it at some variable t here. Then we multiply by e to the minus st, and we integrate with respect to t. So that's the definition of the usual Laplace transform. So the Laplace transform, as we can see, it acts on functions. And this matrix over here, well, at the moment, it's just an array of numbers. It's not really a function. And we would really like to think about matrices as functions because maybe we can extend the definition of our Laplace transform here. So how can we think of matrices as functions? Well, first of all, matrices you can think about as rank 2 tensors with respect to some kinds of basis on your vector space and whatsoever. And there's a couple of rank 2 tensors you could use, but the one that probably makes the most sense for us today is just the endomorphisms. Now, you may think, well, what vector spaces do we need endomorphisms on? Well, since that's with respect to a basis anyways, it's pretty much the same as endomorphisms on R2, so a linear maps from R2 to R2. You could probably, in general, I was thinking about this, you could probably take the Laplace transform of any endomorphism in general without referring to a basis, but yeah, I don't know how to integrate over vector spaces unless measure theorists have their own way of doing those things. I'm not a measure theorist. But yeah, let's not worry about too much of that weird, crazy stuff there. Matrices are functions from R2 to R2. They are linear maps. So perhaps we can extend our definition of the Laplace transform to not only take in functions from R to R, but let's say functions from Rn to Rm or something like that. And that's exactly what we're going to try to do now. The first thing we need to generalize is the first generalization I'm going to make. Maybe what I'll call this L operator here, this curly L, I'm going to call it L with subscripts 1 and 1 here. So maybe I should put 1 here and 1 here as well. The reason why is it's taking functions from R1 into R1, and it gives us another function from C1 into C1, hence the 1, 1. Now, the first thing I want to do is I want to discuss the multivariable Laplace transform. This is something that's used to solve differential equations with multiple variables. The lights just turned off. I don't think that's too much of a problem for the camera, hopefully. But yeah, the first thing we want to do is take a look at L n, 1. So what is L n comma 1. Well, this is going to act on a function, let's call it f, that goes from Rn into R1 like so. So now our functions can have multiple inputs. So we expect that this gives us another function going from Cn into c to the 1 like so. So this guy over here, this is the n-dimensional Laplace transform. And I also need to tell you guys how we define this guy over here. So L, and then we have n comma 1. This is going to take in our function f over here. So this f is different to this f because this is functions that can take in multiple values, or this is a function that can only take in one real number. But anyways, this is going to take in Cn. So we need n complex numbers, let's call it S1, all the way up until Sn like so. Okay. And how do we define this over here? Well, the way you define something like this is to take the Laplace transform n times, each time with respect to a new variable. Well, over here with the one-dimensional case, we have integral with respect to dt. But here we're going to have n integrals, and then we're going to have dt1, dt2, and so on. So we also pick up these e to the minus st factors here. But now it's going to be e to the minus s1t1, e to the minus s2t2, and so on. And we can bring all those exponential factors together in the following way. So first of all, we have n integrals. So integral dot dot dot, and then we have another integral, and this is n times over here. Okay. And then now we're going to have f. F eats n variables, so let's call it t1 all the way up until tn. And then we have e to the minus s1t1. So this is what we would get if we integrate with respect to t1 only, but we want to do it for all the t1s up until tn. So in fact, we're going to have dot 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 here, and then also e to the minus sn tn. And then, yeah, we would have our n integration variables. So that's going to be dt1 dot 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 and then dtn. Hopefully you guys can see all of that on the camera. Okay, and this guy over here, we can probably write it in a bit more of a nicer way. So you may notice we have s1 to sn here. Well, let's just rewrite that as some s vector, so we'll just write it in this fashion like so. And yeah, this is equal to the integral from 0 to infinity. And then this goes n times over here. Okay, then we have the f, and let's write this t1 to tn as t arrow, and then we have e to the minus s1 and blah, blah, blah. And we can combine these exponential factors together, we can factor out a negative, and then you may notice we're going to be left with s1 t1 plus all the way up until sn tn. And that's exactly the inner product, so we can probably write e to the minus, and then inner product of s and t. So this is the Euclidean inner products that we have over here. I'm not too sure if generalizing to inner products or just any inner products would be a good idea in this case, but maybe that's something you could do. And then we have dt arrow, which is just, well, this guy over here. So yeah, that's how we can define the n-dimensional Laplace transform. Now, we're not really quite there yet because we can, at the moment, we can only take Laplace transforms of functions going from Rn to R. We want Laplace transforms of functions going from Rn to Rm, where m is some other integer. So let's try to define that somehow now. Let's go up over here. Okay, I should have probably used the first whiteboard here. Oh well, so let's take a look at the Laplace transform, n comma m. So this guy now, that's going to take functions from Rn and then spit out some m tuple of real numbers like so. And well, we expect this to be a map from Cn to Cm. Okay, so how do we define this guy here? Well, notice, maybe just for good notation, I shouldn't call this f anymore because we're not scalar valued, we're vector valued. So let's call it, let's just write big F over here with a little arrow like so. Okay. So notice our function now, it has m components. So if we try to take the Laplace transform of this, it probably makes sense if we take the Laplace transform of one component at a time. And that's exactly how we're going to define this over here. So if we take the Laplace transform, n comma m, of this f arrow here, then, well, this is going to take in s over here. And we need m components, because we're going to see m. So this is going to be equal to, well, we define this to be equal to, we have m numbers over here, or m functions rather. And each of these functions, well, it's just going to be the Laplace transform of the components of f. And now notice the components of f, the scalar valued. So we're going to be using the Laplace n, 1 here. So this is going to be L n, 1. And then we have f1 of s, arrow. And then we go all the way until we get to L, and then we have n, n once again, f. And now this is the mth component, so fm, and then we also have our s variable here. Okay, so all the f1s to fm, by the way, I might write it over here. We should be able to write our vector valued function as f1 all the way up until fm, because it has m components like so. Okay, so this is what we have now. So what did we just achieve, kind of? We're able to define the Laplace transform of functions going from Rm to Rm. So n and m we can pick as any positive integers we want. But we're only interested in the case where n equals 2 and m equals 2, because we're taking the Laplace transform of a 2 by 2 matrix. And maybe at the end of the video we can extend to n by m matrices, or m by n matrices rather. So now we should be ready to calculate the Laplace transform of that particular matrix with entries A, B, C, and D. So how can we do this? Well, we can just apply the formula down here where n and m are both equal to 2. So the first thing we need to do is take a look at what the component functions of our big F arrow is. So if we consider, let's just take f over here to be equal to our matrix, so A, B, and then CD, we want to take a look at what the components of f are. So in particular, we need to evaluate f on, let's say, T1 and T2. So here I'm using column matrices just to make it look nice with the 2 by 2 matrices here, but really it doesn't really matter if you do row or column. So this is just going to be A, B, C, D, and then we act on T1 and then T2. So this is going to give us the components of our function. Namely, it's going to be A times T1, and then plus B times T2. And then we're going to have CT1 and then plus DT2, like so. Okay, so we have the components. There's 2 components to our function here. And for each of our components there, we need to take the n-dimensional Laplace transform, but in our case, it's the 2-dimensional Laplace transform of both of those linear functions we have there. Okay, so let's try to do that now. And it may seem like there's quite a bit to do. There's a lot of integration. We need to do like 4 integrals here. But it turns out we only need to do 1 integral because, well, all of these we just need to switch around T1s and T2s, A, B, C's, and D's. You'll see what I mean by that later. So let's first of all try to calculate what the n comma, or not n comma, this is 2 comma 1 Laplace transform of, let's say, the first entry. So we have L2 comma 1 of, we have AT1 and then plus BT2. And then we want to evaluate on, let's say, some new Laplace variables. Let's call them S1 and S2. Let's put it in a column as well, just to make it look nice. So let's see what this would look like here. Well, first of all, what is the 2 comma 1 Laplace transform? Well, if we take a look at how we define it here, we need to have 2 integrals, and then we just have a function, and then e to the minus s1t1 minus s2t2. So let's do exactly that. We're going to have double integral now. So integral from 0 to infinity, integral from 0 to infinity. We have our function, which we have over here. So we're going to have at1 plus bt2. And then we multiply this by e to the minus s1t1. And then we also have s2t2. So let's put it over here, like so. Okay, and then we integrate with respect to dt1 and then dt2. Or any order we really want. It doesn't quite matter. Okay, so what can we do from here? We can probably start by splitting up the integral, use the linearity of the integral, split it up across this plus here. And then we can bring certain variables in and whatnot, so we would probably get something that looks like the integral from 0 to infinity of another integral from 0 to infinity, and then we would have, let's put the a out over here somewhere. So we have a, and then we have t1, e to the minus s1, t1, and then we can integrate with respect to t1 first of this guy, and then we still have that extra factor there, so e to the minus s2 t2, and then we integrate with respect to dt2. Okay. And we would have the same thing over here, but we would have b now. So we would get something that looks like b, so this is plus here, so b integral from 0 to infinity, integral from 0 to infinity. Then we would have a t2 now, and then e to the minus s2 t2, and we integrate with respect to, let's say, the t2 variable first, and then we have e to the minus s1 t1, and then dt1 at the end. So basically, these two integrals, they're the same. We just switch around a couple of variables and whatnot. And it's actually not too tricky to evaluate. Let's do the integration up over here. You may notice for both of those integrands there, it's just integration by parts, so nothing too tricky for us, hopefully. So let's just do the usual DI method, the superior integration by parts method. I don't know why they don't teach this at my uni, at least. We have to do the one where you rewrite part of the integral as the derivative of another function. That is the gross. DI is more superior. So what are we differentiating? Let's do the first integral. So this is just t1 over here. And then we have plus minus plus. This becomes 1 and 0. And we are integrating e to the minus s1 t1. So e to the minus s1 t1. If we integrate once, we get minus 1 over s1. E to the minus s1 and then t1. Integrating again, we get positive 1 over s1 but squared. E to the minus s1 t1 like so. And then how does integration by parts work? Well, we just do the diagonals over here. We multiply down and evaluate at the bounds. So, I mean, we don't really have to do it for both of these functions because this integral over here, we can just use the result we get from the first integral, but just change the a to a b and switch the s1 and s2 variables around. So actually, what we're going to do, we're going to rub this out just to save some space here. And then, so this variable doesn't exist anymore. Let's just forget about this for now. So let's see what this would give us. So this would, we would still have a over here. That is not an a, that looks like a q. So we have a. And then we have the integral from 0 to infinity. So here we're just doing the inner integral, not the outer integral yet. So the inner integral, we would have t1 and then minus 1 over s1. So minus t1 over s1, and then e to the minus s1 t1. So that's his first diagonal over here. We evaluate this guy from 0 to infinity. And you may notice if you plug in t equals 0, that's going to kill off the whole thing. If you plug in t equals infinity, you get e to the minus some big number. So that's also going to go to 0. And because s is positive, well, I think this works if the real part of s is positive anyway, so you get 0. So this goes to 0, that's nice. Okay, and we have this other diagonal that's going to give us a minus, and then we have 1 over s2, no, it's s1, but squared. And then we have e to the minus s1 and then t1 like so, and this we evaluate from 0 to infinity. What happens if you plug in infinity? Well, you're going to get 0 because of this exponential factor. If you plug in 0, e to the 0 is 1. So you're left with 1 over s1 squared. And you may think, well, where's the negative? Well, the second part of integration, we also get a negative, so it cancels. So if none of that made sense, just write it out on a piece of paper, and it should make perfect sense. So this should give us a, and then integral from 0 to infinity. And I just realized we've forgotten that exponential factor. So this is big brackets here. And then we still have e to the minus s2 and then t2 and then dt2. Okay, so what does this give us? Let's go down over here. So we have that a at the front still. And then we have the integral from 0 to infinity. We still need to calculate. And then this guy goes to 0. And we said that this guy over here, that was just 1 over s1 but squared. Okay, so we have 1 over s1 but squared, and then e to the minus s2 t2, and then we integrate with respect to dt2, and that's rather simple to evaluate because first of all the s1 squared is just a constant, so I mean we would get something like a over s1 but squared, and then we have the integral of e to the minus s2 t2, but again, that's easy to integrate, so that's going to be minus 1 over s2 like so, and then e to the minus s2 t2, and we evaluate this guy from 0 to infinity. At infinity, this goes to 0 because of the exponential factor, and at 0, we're going to get 1 over s2, but because this is the second part of the integration, we cancel with this negative over here. So in the end, the Laplace transform of just a times t1 with respect to those two variables, s1 and s2, is going to give us a over, and then we have s1 but squared times s2. So that's the Laplace transform of that guy over there, that little guy. Now, that's not the only thing we wanted. We also wanted this bt2 as well as the ct1 and dt2. But yeah, those are really easy to get. We just need to switch some variables around. So we're pretty much very close to being finished here. So let's see, what did we want to do? First of all, we wanted the Laplace transform 2, 1 of at1 plus bt2. That was what we were trying to originally calculate. So if we have the Laplace transform 2, 1 of, we have at1 and then plus bt2. That's with respect to s1 and s2. That is going to give us, well, for the at1, we just found the answer. It was equal to a over s1 squared and then s2. And then for the bt2 one, well, we just need to turn a into b. So we have plus b over here and then over. And since b has the t2 variable attached, we're basically switching t1s and t2s around and s1s and s2s around in all our calculations up here. So really, this is going to give us something like s1 and then s2 but squared. So instead of squaring the s1 here, we're squaring the s2 and we're keeping the other variable, well, just raised to 1 power. So that's what we have. We also needed to calculate the Laplace transform. So that was just the first component, the Laplace transform of at1 plus bt2. That was just the first component of our function. So far, we've only calculated this guy over here. That was the guy that we calculate so far. We also need to calculate this second guy over here, which is taking the Laplace transform of the second component. So what on earth is the second component? Well, we found it up over there. It was ct1 plus dt2. So let's do the Laplace transform of ct1, and then plus d, and then we have our t2 now, and we have s1, s2 once again. So what is this going to give us? Well, it's pretty obvious what this would give us because we're just changing a's to c's and then b's to d. It's really quite simple. So this is going to be pretty much the same thing. We have c over s1 squared, s2, and then plus d over s1, s2, but squared. So that's quite nice. Now, we're pretty much almost done now. We just need to put all these guys into one big matrix, and then we're pretty much done with the calculations. However, there is something a little simple we can do from here. Namely, we can combine these two fractions together. And how can we do that? We can just multiply the first fraction by s2 over s2, the second fraction by s1 over s1. So this is going to give us something like a times s1 plus b times this is s1 over here. And this guy over here, that's supposed to be the s2. And this is divided by s1 squared and then s2 squared. Okay, and the same thing goes down here. We have cs2 and then plus ds1 over s1 squared and then times s2 but also squared, like so. So that should be it. If you combine those two fractions together. And now for the grand finale, I guess, well, not really the grand finale yet, the final result for this section at least, we wanted to take the Laplace transform of that matrix. So we just need to put both of these results over here into just one big tuple, this 2 tuple over here, like so, as we have in our calculation. So that's not too tricky to do. Let's write this as a column matrix. So finally, we have the Laplace transform of the matrix. We have AB and then CD. What is that going to be over there? Well, we need some S variables, let's say S1 and then S2, as we have before. Well, this is just going to be, notice we can factor out S1 and S2 squared on the denominator. So we have 1 over, we have S1 squared, S2 squared, and then we also have, well, we just have the linear stuff in our matrix. So we have A S2 plus B S1. And then we also have C S2 and then plus D S1. And that's pretty much the final result. I guess one more nice simplification you can do for the 2 by 2 case is you could have 1 over S1 squared, S2 squared, and you can rewrite this guy over here as a nice matrix equation, kind of, but you can write this as we would have B and then A over here, then D and then C, because the variables of S1, S2, they're kind of reversed, and then we would have S1 and then S2. So I guess we'll just leave this as the final result over here. This would be the Laplace transform of a matrix. So as you can see, the matrix is a linear function from R2 to R2. And of course, the Laplace transform does not necessarily preserve the linear function over here. For example, just in the one-dimensional case, the Laplace transform of t is 1 over s squared, I think. Yeah, 1 over s squared. So it doesn't really preserve that. And as you can see, if we have 2 dimensions over here, we also have s1 squared, s2 squared. So there are some similarities. And then you also have this linear bit here. So yeah, that's the Laplace transform of a matrix. You can probably extend this to n by n matrices as well. We can try this right now. So if we have the Laplace transform, let's try to do this following matrix. So let's do, we have something like A, this is 1, 1 here, and then dot, dot, dot. Let's say we have A, well, this is row 1, and then column, how many columns should we have? We should have n over here because n variables. Then we have dot, dot, dot. Let's do a m1 over here, and then dot, 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 and then we also have a mn. So let's try to do this matrix over here. So this is a, m by n matrix, I believe. Yes, no, m by n matrix is m rows and n columns. I always get confused about which ways which. But yeah, what would this look like? Well, it's not too tricky to see. This would also have n variables, so s1 dot dot dot, and then sn over here. So what would we have? Well, first of all, we still have this factor. This is 1 over s1 but squared, but we go all the way up until sn, but then we square this. Okay. And then what happens in this matrix over here? Well, remember, because we had to kind of combine everything together. So here, if we take a look at this first, the variable, we had to multiply by all the yeses that weren't the first one, if that makes any sense. So here, we would actually want a and then 1, 1 here, and then we have s2 all the way up until sn, something like that. And then we have plus all the way. So here we have A11, then we would do A12, next A13, all the way up until A1n. But then once we get to A1n, well, we want to have S1, and then all the way up until Sn minus 1. Because this is the nth variable, the A, it's the nth one, so we have to multiply by all the s's that are not the nth one. And then we can go all the way down over here, down like so. And then we would just copy the same thing. But now instead of A11, we have AM1, and then we have S2 dot dot dot, and then Sn, like so, plus dot dot dot. And then we have, S1 dot dot dot, Sn minus 1, and then what we would have, Mn, like so. And we can close off the matrix there. And that would be the Laplace transform of a, what is it again? An m by n matrix. Like so. This is the m by n case, and this guy over here, this is the 2 by 2 case. So we've basically covered all of it over here. We not only know how to do the Laplace transform of a 2 by 2 matrix, we can also do it with any matrix of any size we want, pretty much. But yeah, that's pretty much all for this video, I guess. Don't know if there's any proper applications of this, probably to solve systems of partial differential equations or something like that. I really don't quite know. But yeah, if this thing over here, whatever it is even used, then it's probably not very useful on its own. For example, with normal Laplace transforms, if you want to solve differential equations, you have to consider Laplace transforms of many different functions that go from R to R. But here, we only considered a special case of a function which goes from R2 to R2. So that's probably not very useful. You have to also combine it with other functions, or the Laplace transform of other functions that go from R2 to R2. But yeah, I found this pretty cool. Next week though, if I still have time, we'll do the Fourier transform of a matrix. So make sure you subscribe so you don't miss out on that there. But yeah, that's pretty much all for today. Hope you guys enjoyed. And yeah, up until the next one, have a wonderful day, and I'll see you guys next time. Bye-bye. So that's pretty much the video. You guys have dismissed now. You don't need to keep watching. Video's over, unless you want to watch me clean these blackboards here, which is probably something I'll put in the video for fun. So yeah, let's clean blackboards now. These blackboards were actually atrocious before I came here, because yeah, I'm in a tutorial room right now. It's not the best tutorial room because it's pretty echoey, so I have to wear a lav mic here. I can't use my usual microphone. But yeah, these blackboards, did I say whiteboard before? I feel like I always say whiteboard instead of blackboard, but yeah, these blackboards were atrocious because no one cleans them. Because we don't have those proper swiggy things, I think that's what it's called, those little wiper things that you usually see professors on YouTube and whatnot use. But yeah, we don't have those. We only have these mops over here. And I actually had to go to the bathroom and wet one of these so it can actually use it to clean these blackboards. But yeah, we don't have those little swiggy things, so students never clean them properly if they ever use them. We do have whiteboards all over this classroom though, so people usually just use whiteboards, but no one uses blackboard because they're never cleaned properly. And even if you do try to clean them without water, so just using these rags over here, you still leave these chalk marks everywhere. And then, yeah, it just builds up over time. Like before I came here, you can tell that these are blackboards. Haven't been cleaned for years, probably. I wouldn't be surprised. So we'll see how these blackboard videos go. This is my first time filming on a blackboard. Actually, I tried doing it last week, and it didn't really work out too well because I had microphones issues and whatnot, so this is actually a re-recording here. So hopefully this one turned out fine. So if you see this video here on YouTube, that means yeah, everything worked out well. Complex analysis stuff is still coming, by the way. I just don't have time to film it yet. Should I film complex analysis stuff on the blackboards? Would that be something interesting, or do you guys reckon whiteboard complex analysis is better than blackboard complex analysis? I really don't quite know because it's easier drawing contours and whatnot on whiteboards, I think. I haven't tried drawing the contours on blackboard though, but maybe, yeah, that could work out. And on the blackboard, we only have white chalk here. There's no colored chalk, so I can't do the usual thing with the colors and whatnot. I really don't quite know. The university should really put swiggies into every room with blackboards because yeah, cleaning the blackboards with mops takes forever to do. I spent like 5 minutes. I actually spent 10 minutes the other day cleaning the blackboard before I tried to film a video. This is not the cleanest blackboard, but yeah, I'll clean it better next time before I film the video because the mop is running low on water, so it's not picking up all the chalk dust. Or maybe the mop is just so dirty from all the chalk on it that when I wipe it, well, it leaves chalk that are rubbed off behind. But yeah, we'll call it a day here. That's the end of the video. Goodbye.